This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, the professor for this class. And we're at lecture 42, the second part of our two-part series of lectures on diffraction for lithography. As we saw last time, we can get diffraction patterns for any given mass pattern, and we actually derived the diffraction pattern for an isolated space. And here's our answer over here. And we arrived at that by recognizing that the far-field diffraction pattern, the Fraunhofer diffraction pattern that we get a long ways away from the mask, is equal to the Fourier transform of the mask transmittance function. Right? So here's the mask transmittance function, T sub m of x, and it's pictured here as being very simple. It's 0 underneath the dark regions of the mask, and it's 1 underneath the clear regions of the mask. So for an isolated space, we have an isolated square pulse for our mass transmission. Now, these pictures are cross-sections of the mask, and we're assuming they're infinitely long in a direction in and out of the page, or in and out of the screen. So this is a small space. We call it a slit when we're talking about just light diffraction in general, but from the perspective of lithography and our mask pattern, we would call this a space, an opening in an otherwise opaque mask pattern. And when we took the Fourier transform, we went through the math, and we calculated then the diffraction pattern, which I call this capital T sub m, as a function of the spatial frequency, f sub x, and that's a scaled coordinate in the diffraction plane. And the answer is this sinc function, sine x over x function, and it's graphed here. So we went through the details of how to calculate that diffraction pattern using the Fourier transform. And this is a very simple example. Another example, which we're going to talk about in this lecture, is a repeating pattern of lines and spaces. This is another very common mass pattern. We often have patterns that repeat over and over again. Here we'll have a line and a space. So the line is the dark region, and the space is the clear region. Again, this is a cross-section of the mass, so these lines and spaces continue on in and out of the board. And our mass transmittance function is a square pulse, 0, 1, 0, 1, repeating over and over again. The pitch is the repeating distance, so the center of the line to the center of the next line, or the center of the space to the center of the next space. That would be the pitch of this pattern. And the resulting diffraction pattern looks very, very different. There are some similarities to the isolated space, as we'll see, but it looks very different indeed. Instead of getting a continuous energy distribution, what I'm plotting here is in fact the amplitude of the electric field, but in the case of a repeating pattern of lines and spaces, instead of getting a continuum of light energy or electric field, we get instead discrete points of light. And these points of light are represented by these arrows. Right? So it's a little point of light, but I use the height of the arrow to represent how bright that is. In fact, the amplitude of the electric field at that point of light, I use a little arrow to represent that amplitude. So I get discrete points of light rather than a continuum of light. Mathematically, the answer looks like this, and it has this strange thing called a delta function, which we're going to look at and try to understand a little bit. Instead of going through the math, instead of deriving this equation using the Fourier transform, which we could do, it's a little bit hard, but not too bad. Instead, I want to try to understand why we get these discrete points of light from a physical perspective rather than a mathematical perspective. There's our answer, so we know what the answer is mathematically, but why does this happen? Why do we get discrete points of light? And what can we learn about these points of light? To answer that question, we're going to start with something else. We're going to start with the topic of interference, because diffraction and interference are closely coupled. The reason we get interesting diffraction patterns is because of interference. And what is interference? It's simply the way two beams of light or two waves of light add together. Whenever I add two waves of light together, I say that those two waves interfere with each other. So let's take a look at a simple example, something we'll call constructive interference. I'm going to add two waves of light that are traveling in the same direction, and they overlap and they combine with each other. I'm going to add them up when they're in phase. First of all, what does that mean? Well, here's a cosine wave. It has a particular frequency, f. The period is 1 over 2 pi f, which in this case we would call the wavelength. The cosine function is our wave. Now I have a second wave that I'm going to add to it. And this second wave will be in phase with the first wave. In other words, it will be identical. I'll assume these two waves are exactly the same. They're in phase so that they're, whenever we're at a trough or a bottom of the wave, and in one of them I'm in the exact same bottom of the wave of the other, and the peaks of the two waves line up as well. Everything is in phase, we say. The peaks and the valleys line up. I add these two together, what am I going to get? Well, I can add cosine plus cosine. It's pretty simple. I get 2 cosine. In other words, I get a wave that looks just like the other waves, but just greater in amplitude. The amplitude of the original 2 cosines was 1. Remember well, not remember, but you should recall that the amplitude of the sinusoid is the thing that multiplies the front. All right, the frequency, 2 pi fx. This is the spatial frequency f of the sinusoid. And now, when I add these two together, I get an amplitude of 2. In other words, when the two waves are in phase, and I add them together, they interfere constructively, giving me a new wave that has a greater amplitude. That's called constructive interference. Destructive interference, what does that mean? It means adding two waves that are out of phase. So I'm going to take this wave that we saw just a moment ago and add to it an identical wave that has been shifted in phase by half of a wavelength. That is, shifted in phase by pi. So mathematically, I have the same cosine with the same frequency, but I add a phase shift of pi. Pi is the same as 180 degrees, which is half of a cycle, or half of a wavelength in terms of the distance from peak to peak. And sure enough, when I look at the trough of one wave, I see that it corresponds, it lines up with the peak of the other wave. So what's going to happen when I add these two together? Well, every place that the first wave is positive, the second wave will be negative. Every place the first wave is negative, the second wave will be positive. When I add these two things together, I get exactly 0. Another way to think of it is you look at one of your trigonometric identities and say cosine 2 pi fx plus pi is nothing more than equal to minus cosine 2 pi fx. And so when I add these two things together, I'm really subtracting a cosine from a cosine, and I get 0. Since each of these waves are real waves of light in our representation here, adding two waves of light that are out of phase, where one's high when the other's low, and vice versa, when they're out of phase, they add together and cancel out. We call that destructive interference, and we get darkness as a result. Now, with those two ideas in mind, let's look at how light diffracts from a masked pattern of equal lines and spaces. So here's our diffraction example. I'm going to shine light on this masked pattern, and this light will be a normally incident plane wave. Normally incident means it hits the mask perpendicular, and it's a plane wave. That means the wave front forms a plane. That is, all along this plane of incidence is a surface of constant phase. So the light has identical phase everywhere as it strikes the mask. We will call that later coherent illumination, but we'll worry about the definition of that term why I'm applying it here later. For now, we'll just think of it as normally incident plane wave of light, so all the light has the exact same phase when it hits these openings. Now, I am going to look at what the diffraction pattern is some long ways away. I'll call that the observation point. It'll be a long ways away from the mass, so I'm in the far field where Fraunhofer diffraction applies. And I'll ask, what do I see? If I'm looking at the light coming out of this mask at this observation point a long ways away, what do I see? Well, I'll see some light coming from, say, this hole. And to reach my observation point, it must exit this hole at some angle theta. But that's not all of the light that I'll see. I'll see light from a neighboring hole, or this space next to it. And that light will also come out and reach my observation point. I'm going to concentrate on just those two spaces and light coming from those two spaces. But in fact, I'll extend the analysis to light coming from all of the spaces as it diffracts or emerges from these spaces on the photomask. If my observation point is a long ways away, I can approximate these two rays of light as being parallel. And that will be the equivalent of making the far field approximation, or the Fraunhofer approximation. I'm far enough away compared to the pitch P that these two rays can be thought of as being parallel. Now remember, the pitch P is the sum of the line width and the space width. So here's the line width, the opaque region, the space width, the clear region, and the pitch will be the sum of those two. I'm going to assume that I have equal lines and spaces. Now, what's the difference between these two rays? Well, the only difference is a path difference. If I drop a normal down from this ray to this one, 90 degrees when it hits, I see that from this point on, from here on, those two rays travel identical distances. So from there on, everything is the same between those two rays. But you see that the ray on the right here travels an extra distance that the second ray on the left does not. What is that distance? Well, let's look at the geometry. First of all, this angle theta, a little bit of thinking about it will show that the angle theta here is equal to the angle theta here. And therefore, what I want to know is, what is this path difference? The extra path length that one ray travels that the other doesn't. Well, now it's just a simple matter of trigonometry, the definition of a sine. The path difference is nothing more than the pitch, which is the hypotenuse of this triangle, times the sine of that angle. Okay, well, what can we learn about this? What I observe at my observation point will be the sum of these two waves. And I know something about how two waves interfere with each other. If they're in phase, they interfere constructively. If they're out of phase, they interfere destructively. So I'm going to ask, what is the condition that would enable these two rays to interfere with each other constructively in phase? And the answer is, if the path difference equals a wavelength, they'll be in phase. Why do I say that? Well, a path difference equals a phase difference. As light travels, its phase changes as it moves through position. Every wavelength, it goes through a cycle of 360 degrees, or 2 pi. So every wavelength of distance traveled corresponds to a phase change of that light of 2 pi. If it travels half of a wavelength, it's changed by a distance of pi. If it travels a quarter of a wavelength, it's changed by a distance of pi over 2. So the distance traveled determines the phase change of the light as it's traveling. So what if this particular path difference happened to be exactly equal to 1 wavelength? Well, the light at this point and at this point are in phase because my normally incident plane wave says they are. If this light travels 1 wavelength farther, by the time it got to this point, it would be back to being in phase again. From this point on, it travels the same distance from here on and from here on. They stay in phase. So if this path difference is a wavelength, then I will get constructive interference. In fact, if the path difference is any multiple of the wavelength, I will get constructive interference. So let's think about the angle to my observation point as theta sub n. I'll explain what I mean by n in just a moment. And I'll ask, what's the condition? What angle will allow me to get constructive interference? Well, it's an angle such that the path difference, pitch times the sine of the angle, is a multiple of the wavelength. That's where n comes in. There's not just one angle that will allow constructive interference. There's lots of angles that will allow constructive interference. What are those angles? All the angles such that p times the sine of the angle is a multiple of the wavelength. We'll let that multiple be n, and we'll give that n a name. We'll call it the nth diffraction order. So n is the diffraction order number. When n equals 0, we say that we have the 0 order. And if I plug in n equals 0, what angle do I get? I get an angle equal to 0, theta equals 0. So the 0 order is the light that goes through without changing its direction. And that results in constructive interference and a bright point of light. When n equals 1, I get the first diffracted order. So I plug in n equal to 1, I get a particular angle that comes from solving this equation, p times sine of theta equals 1 times lambda. That gives me the first diffracted order. I can have a negative 1 as well. That's simply an angle coming off in the other direction. N equal to minus 1 is the minus first diffracted order. And I simply plug in the equation n equal to minus 1. I have a minus 2 and a plus 2, a minus 3 and a plus 3. All the integer values of n produce a different angle that allows for constructive interference. We call these the diffraction orders, and they result in bright points of light only at those specific angles. We can express these angles in terms of spatial frequency. You might recall, you should recall, that the spatial frequency is the sine of the diffracted angle divided by the wavelength. So the spatial frequency at which I get bright points of light are multiples of 1 over the pitch. So every time the spatial frequency is some multiple of n divided by the pitch, then I'll get a bright point of light. And those are the diffracted orders, and that's the diffraction pattern that we're going to get for the case of a periodic pattern of lines and spaces. In fact, every time we have a periodic mask pattern, we will get discrete points of light because of this interference phenomenon. Whenever I have an isolated pattern, a pattern that does not repeat, then I'll get a continuum of energy in my diffraction pattern. But whenever my mask pattern is a repeating pattern, it repeats over and over and over, I'll get discrete points of light or diffracted orders for my diffraction pattern. Now, that tells us where the diffracted orders occur, but it doesn't tell us how bright they are. To get the amplitude of each diffracted order, I have to go ahead and do the math. I have to plug in the transmittance function of the mask into the Fourier transform and work out the calculations. Well, somebody's done that. I've done that. I won't make you do this here, but it's just something we do. We work out the math and we get our answer. The answer is the diffraction pattern is the sum of these Dirac delta functions multiplied by an amplitude. The amplitude is none other than the sinc function at that particular frequency. Remember the sinc function, it's the diffraction pattern of an isolated space. It was pi times the spatial frequency times x divided by the spatial frequency times pi. Well, for the case of spatial frequencies equal to n over the pitch, then we see that we will get an amplitude that's equal to that sinc function. Now, for the case of equal lines and spaces, I know something about W over P. W over P is 1/2 if I have equal lines and spaces. So now my general repeating line space pattern amplitude becomes very specific values when W over P is 1/2. Why? Because this is sine of some integer times pi over 2. And I know what those values are. First, n equal to 0. I have to do a little bit of a limit. And the limit as n goes to 0, I find that the amplitude is 1/2. I find that for all the even values of n, the amplitude is 0. For even values of n, I get multiples of pi, and the sine of pi is always going to be 0. So for even values of n, the amplitude of my diffraction order is 0. That's only true for equal lines and spaces. But for other duty cycles, for other widths not exactly equal to half the pitch, then the even orders won't be exactly 0. For half of the odd orders, n equal to 1, 5, and 9, etc., I get 1 over n times pi. And for the n equal to 3, 7, 11, etc., I get minus 1 over n times pi. Those are the amplitudes of the diffracted orders. And the orders occur at spatial frequencies equal to some multiple of n over the pitch. And that comes through with this delta function. All right, now you've probably already been sitting there thinking, what is a delta function? What does that mean? What does it mean physically? What does it mean mathematically? So let's stop here and talk about the delta function. Hopefully you've seen delta functions before. It's a very, very useful mathematical tool. Let me explain what a delta function is mathematically, and I'll also explain what it means physically in this problem. What's a delta function? I'm going to generate a delta function in a very simple way. Looks like a big fancy equation here, but I'll explain that equation in terms of a graph instead. And here's what I'll do. Suppose I have a unit area rectangle centered at x naught. All right, so that's it. This is a rectangle. Here's the x-axis. The position along the x-axis where this rectangle is centered is x naught, and the area of the rectangle is 1. All right, so it has some width, epsilon, let's say, and height will be 1 over epsilon, because I want to keep the area equal to 1. All right, we all know what a rectangle looks like, but what do you think would happen if I were to cut the width of that rectangle in half while simultaneously doubling its height? What did I do? Cut the width in half, double the height, so the area remains 1. All right, now I just have a new rectangle. It's narrower and taller. Okay, do it again. Cut the width in half and double the height. The area is still 1, isn't it? Cut the width in half, double the height. The area remains 1, but this thing is getting narrower and narrower and narrower and taller and taller and taller. If I do that forever, what I have is a delta function. I have a function that has 0 width, infinite height, and unit area. That is all a Dirac delta function is. A function with 0 width, infinite height, and unit area. Mathematically, so far so good. Physically, I will use the delta function to represent an idealized point of light. An ideal point source is a real point. It has, it goes infinitely small in its dimension, its width, but it has unit area. That is, it has a certain amount of energy in that point. I don't let the the energy become infinite. I don't let the energy go to zero. I say the energy is a certain value. I'm just mathematically thinking of the size of that light source to be a zero width. So delta functions represent idealized points of light. Some important properties of the delta function that we're going to have to use very soon. First, if I wanted to define what a delta function was, I simply say a delta function is zero everywhere except at the origin, and a delta function has unit area. That's what these two lines mean. Delta function is zero everywhere when x is not equal to zero, and if I integrate this delta function I get 1 that has a unit area. Well, that implies that it has infinite height, so we don't need to specify that extra element of description for the delta function. That's the definition. Here's an important property called the sifting property of the delta function. Suppose I have a delta function. I multiply it by any arbitrary function that's continuous at x0. That is, it doesn't have any discontinuous jump at the value x naught. So f of x is continuous around x naught. I multiply it by this delta function and I integrate. What do I get? What I get is the value of this function at the position of the delta function x naught. This sifting property is going to be very useful to us when we use when we allow the diffracted light to go through a lens, which is coming up soon. So I'll give you this property now. But let me tell you something. This is the easiest integral you'll ever do. I didn't even have to do the integral. I simply said, oh, look, I'm taking a function and multiplying it by a delta function and then integrating. All that means is I can take the function out and evaluate it at the position of the delta function. I promise you this will be the easiest integral you've ever done. And we're going to use these easy integrals in the math to come. All right, so much for properties of the delta function. Let's think about it physically again. The delta function represents a point of light. How do you graph a delta function? Well, if you graph its height, you're going to use a lot of graph paper because it goes up to infinity. So I'm not going to graph its height. Instead, I'm going to graph a delta function by drawing an arrow. All right? So whenever I see an arrow, when I should be drawing the amplitude, the arrow tells me, oh, that's a delta function. It really has zero width and infinite height, but what I'll graph instead is the thing multiplying the delta function. Right? Because this has unit area, so the thing multiplying the delta function tells me the amplitude of the point source. Right? The amplitude of the electric field associated with that point source. So that's what I'll do. I'll simply plot an arrow whose height is equal to the thing multiplying the delta function. So what does my diffraction pattern look like? I get a delta function for every time I get constructive interference. That is, I get a point of light whenever I have constructive interference. According to Bragg's condition, constructive interference occurs whenever the spatial frequency is a multiple of 1 over the pitch. So I get a 0 order of light, first order of light, second order of light, third order of light, minus first order, minus second order, minus third order. Now notice that the even orders, the +2 and the -2 orders, have 0 amplitude. That's because I happen to be looking at equal lines and spaces here. Again, if I had a space width that wasn't exactly equal to half of the pitch, then I would get an amplitude for the even orders that wasn't exactly equal to 0. So this becomes a graph of the diffraction pattern for equal lines and spaces. If you want to see what this looks like in real life, you can do a little experiment to generate this diffraction pattern. I'll tell you how. In fact, I'll post on the website for this class a laboratory that you could perform to do some measurements based on this experiment. But here's the simple experiment. Take a CD, music CD, or a DVD, or even a Blu-ray disc, any disc, and then on the information side, you'll see grooves in that disc. These are grooves that are the tracks for the information. Then the information itself on the disc, the bits, ones and zeros, are little pits in those grooves that record the digital information on the disc. But what we're going to do is use the grooves as a diffraction grating. We're going to use the grooves as a pattern of lines and spaces. So take your CD, take a laser pointer, and bounce the laser off of a spot on the CD. Hold it up close to a wall to look at the diffraction pattern that results, and you will see this diffraction pattern. Bright spot in the center, two spots to either side that are a little bit dimmer, on and on. If it's a dark room, you'll be able to see out to the third diffracted order. Probably not further, because the orders get so dim that it becomes hard to see just with the eyes. You'll need some sensitive equipment to detect them. But nonetheless, you can generate this diffraction pattern directly with nothing but a laser pointer and a CD or a DVD. So I recommend you try that. One last thing before we're done with this lecture. How does the pitch on the mask affect the diffraction pattern? Of course, on the mask I could have really big lines and spaces that are spread far apart, or I could have really small lines and spaces that are very close in. What does that do to the diffraction pattern? Well, you see that the position of the diffraction orders goes as one over the pitch. If I have a bigger pitch, then all my diffracted orders move in closer to the center. If I have a small pitch, then my diffracted orders spread out further away from the center. This is going to be a general rule. Small features diffract more. Going back to our isolated space, the first example we saw, we get the exact same thing. If I look at a small isolated space, then my diffraction pattern is spread out. I look at a big isolated space, like here, and my diffraction pattern squeezes in. And that's this W in the equation. So you can type this equation into Excel or something and play around with different values of W, and you'll watch the diffraction pattern spread out and squeeze in. Small features diffract more. This is one of the most fundamental things about lithography that we need to understand, because our goal is going to be to print smaller and smaller features, and the fact that small features diffract more is going to play an intricate role in our understanding of the concept of resolution and how small a feature we can actually print with our imaging tools. All right, we talked about a lot of things in Lecture 42. What have we learned? See if you can answer all of these questions easily. If not, go back and review some of the material. So, define constructive and destructive interference. What is Bragg's condition? What is a delta function? And what does it represent physically in the case of optics? What is a diffraction order? And when do they show up in diffraction patterns? And finally, how does the size of a mask pattern affect its diffraction pattern? Well, we've gone through now in the last two lectures a discussion of diffraction patterns for two example mask patterns. Next, we'll see what happens to this diffraction pattern. It's going to propagate into a lens. So next time we'll start understanding what the lens does to the light. Till then.